Okay, so we're going to look at number 6, which is on the review. And it wants you to find a polynomial function with integer coefficients. So that means positive and negative numbers. No fractions. That has the given zeros. So 1 plus I times the square root of 3, and then 2 and 2. So we know 2 and 2 would be a double root, since they're repeated twice. So I'm going to write those as x minus 2 squared. And then if we have 1 plus I square root of 3, how do we write that as a factor? Kevin?
X minus 1 minus I squared 3.
Right. And then you have to do the other one because they always occur in pairs, right? So anytime you have imaginary numbers, they always occur in pairs. So if you have 1 plus I square root of 3, then we also have the opposite. The Apple TV and I are not friends today. All right, so now that we have this information, when you're multiplying the conjugates together, you need to treat these as a group of terms because those are your real numbers. And then we have the imaginary numbers that makes the conjugate part. So these are grouped together, x minus 1, that's the real part. And then we have the conjugate part. Kevin? Yes, of course. So foiling the like pieces together, if we have x minus 2 quantity squared, Ellie, what does x minus 2 quantity squared give us?
X squared minus 4x plus 1.
All right, so that's one factor that now is expanded, so I'm going to put parentheses around it. And then the other two conjugates, multiplying these two pieces together. So if I do that, I get x squared minus 2x plus 1. The middle terms cancel because they're conjugates, and then I would multiply the last two pieces together. What would I times the square root of 3 with a negative I times the square root of 3 become? Okay? Yeah, so negative 3, square root of 3, square root of 3, that's the negative 3. And then she said I squared. So, Odette, if I simplify all those, because they're all together, those are part of my imaginary zeros. Odette, what would that equation become then?
X squared minus 2x plus 4.
Excellent. Some of you are like separating that, and you're not including the imaginary number as part of the x squared minus 2x plus 1. But that all goes together because that comes from two zeros, and we're pulling those two zeros together. So make sure you're pulling all of that information together and simplifying that equation as well. So now there's a lot of foiling involved because I have a trinomial that I'm foiling with another trinomial. So how many pieces will you have when you're done if you expand all this? 9. So you should have 9 pieces when you're done. And I would say just treat it as like you're using the distributive property. So starting with the x squared, we're distributing through. So there's my x squared term. And then I would go to the middle term and distribute it through everything in the back. And then finally my last term is the plus 4. So distributing that as well gives me a 4x squared minus 8x and then plus 16. So it's big because I just took 3 terms and I multiplied them by 3 terms. So essentially each of the first need to be distributed through the back 3. Connor, what did you get as a final answer?
X to the 4th minus 6x cubed plus 16x squared minus 24x plus 16.
Connor, do you have an f of x in front?
Yep.
Oh, but you're not going to do that mistake on Monday, right?
I will not.
Excellent. Don't forget your f of x. Or y. Something to make it an equation, a function.
So, say like you have to find the vertical asymptotes, would you have to say like x equals, or just you just put the number x equals?
Because it's a line. The number is not a line. the negative 3i squared, that became, so this part here became a plus 3. And we added it with the plus 1. That's how we get the 4 here. So that's how it becomes 4. So negative 3i squared, the I squared is a negative, it's already a negative, so it's a positive 3. You add that with the 1. So it shouldn't be separate, it gets grouped together to create this equation, x squared minus 2x plus 4. Other questions that you'd like to see from every? Sure. Which one would you like to see? Yeah. I just need to pull that up. So if you look, I think it's page 58, right, Abby? 58? So if you look at page 58, this is a really good problem to go over, Abby. So this one says find exactly all the zeros, which should be 4, given that 1 plus I is a 0. So the goal is to use the 0 they give us to algebraically find the others without a calculator. So if you know 1 plus I is a 0, Rebecca, what else do you know? Yeah. So we know that 1 plus I is a 0. So we know 1 minus I is a 0. If I have 2 imaginary zeros, what can we do with those 2 imaginary zeros? That would give us information about the problem, besides the fact that they're zeros, because they told us that. So what can I do with these zeros? Think. Yeah, we're going to change them into factors. So just like we did with the last problem, we'll make them factors. And Quinn, with those factors, what are we going to do, do you think? Yeah, so this is such a good problem because it kind of goes through a lot of the concepts that we talked about throughout the whole chapter. So we are going to FOIL them together. Again, grouping them just like we did before. So that x minus 1, the real part, we're going to multiply. So that's x squared minus 2x plus 1. The imaginary part, we're also going to multiply. So I have negative I squared. And then remember, this negative I squared is really a plus 1. So I still need to continue to get an equation from this, which would be x squared minus 2x and then plus 2. So that's the equation that you have from these zeros. Our goal is to use this equation and the given function to get the other zeros. Now you can't see them in your calculator, but like we want to use this equation to pull out the other zeros. And Quinn said we would use long division to do that. So let me make myself some room here. A little bit of long division. So without me asking a separate long division problem, I can kind of look at 2 different things in one problem here, seeing if you can multiply and divide. And I'm going to write that x squared term that isn't there. I'll write that down just so that I have like terms. So a little bit of long division, Mackenzie. How do we do long division? Yeah, so x squared times what makes x to the 4th? X squared. We have died. And then multiply x squared by those 3 terms. The subtraction. Good?
Yeah.
You just want to take the pass with you, keep it as a souvenir. I'm not sure you want to keep that as a yeah.
That would be appropriate. Just kidding. I do what you mean.
All right, and then when you subtract, your x to the fourth goes away. Negative 2x cubed minus a negative 2x cubed also goes away. And we have a 0x squared minus 2x squared. So we end up with negative 2x squared. Because two terms canceled and I'm using a trinomial, I have to also bring down two more terms. We have an x squared, we want to make it negative 2x squared, so I multiply by negative 2. And then I have the negative 2x squared plus 4x minus 4, so that when I subtract, I get a big fat 0 at the bottom. Big fat 0. So what's left up here? What does that tell me about the equation?
That's that equation represents like the other zero.
Yeah, that represents my missing zeros. So if I set that equal to 0 and take the square root, I now know that I also have zeros at plus or minus square root of 2.
Did you use something?
No.
I didn't.
So the problem with using synthetic division means that you found that 0 using the calculator, and you're not using the given 0. Unless, did you divide with 1 plus I?
Yeah.
Yeah.
Oh, okay, then yes. If you divide with 1 plus I, yeah, that works. Yes. Sure, you can use synthetic division as long as you're using the 0 that they
Yeah.
give you. And then you did that twice.
Mhm.
Yes, yes. Perfect, that's fine. Sure. That works. I think it is the hard way, but I mean,
I don't.
hey, you don't like long division? No.
It's too confusing.
Any other questions from the review, Connor?
Just for number 4 on page 60, is there any algebraic way that we're supposed to find the maximums and minimums?
No.
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 And then also, like the max is up at 137 for the y. Should we scale our graph or can we just draw the dot?
Just draw those little dots. Yep. Make sure it looks lower than the other one that's there.
I changed the scaling.
That's
I
fine.
did it by 20.
What?
Actually,
Just draw those little dots.
Oh my
we
god.
scaled the entire graph so that everyone can fit.
Well, I mean, that's okay. But you don't have to. Scale it. From this page? Yeah, this one. All right, so if you look at number 3, this one is a good one too. Because you've done so much with division and synthetic division and all this wonderful foiling that you forget about the factoring. Just the plain old factoring. So this says to write f of x as a product of linear factors, which is another way of saying factor completely. So if I'm having linear factors, I need to factor completely. When it's a trinomial, that's 3 terms. That's the regular old AC method. So basic factoring, which does, like, you just forget about because it seems so basic once we've learned all this other type of dividing and factoring. But this does just factor using the negative 28. So what two numbers multiply to be negative 28, Kevin?
-7 and +4.
-7 and +4. But Kevin, when you write your factors, because it says x to the 4th,
That's the x squared minus 7 x squared plus 4.
right, -7 and then x squared plus 4. So these are quadratic factors because they're both still x squared. And right now I have quadratic factors that are listed as integers. But it wants us to completely factor it, so I need to take each one of these parentheses and just continue to break them down. Which means if I solve them and get rid of the x squared, then I have plus or minus square root of 7. That goes first because it's a real number. And then again, solving the next one and taking the square root of -4 is 2i, so plus or minus 2i. That has to go second, that's the imaginary numbers. Oops. Don't forget your f of x. Completely factored. So that one seems to be the one that people forget about. Like just the regular old factoring. And it seems like it was so long ago.
Take your best.
I know, right? Alright, so if you find that you have other questions, feel free to shoot me a reminder over the weekend. Stop by on Monday morning because you realize after looking over things that you want to ask a couple other questions. I strongly suggest you go back and look at section 2.1 to 2.3 review in the packet. In the middle of the packet, it's already done. Just look over it. I also suggest you look over the word problems that we did in the packet. There's a couple of application pages for the word problems that we did as homework. So we skipped over some applications in there, but we did still do some in like the homework assignment, so I suggest looking over those. Monday's test is 65 points. 65. Questions? So we are going to start chapter 3 today, and I promise today is a very basic intro to chapter 3. So far, we have covered quadratic functions, polynomial functions, rational functions. We did a little bit of radical functions, so I've just named 4. We did absolute value functions, linear functions. Essentially, we've done everything that you've done last year. We have one more pair of functions to talk about, and that would be the exponential function and the logarithmic function. And then we've done all of the functions from Algebra 2, but you know that we've definitely covered them more thoroughly. We've dug a little deeper. We've gone a little more complex with what we did last year. The applications have been a little more involved. After we're done with this chapter, we've covered all the functions that we can cover in pre-calc. We will start trig. Right now, I think it's November 9th that we start trig, or November 10th.
That's not that far away.
Not that far away at all. Chapter 3 is pretty quick. Like, it's a really thin chapter. 5 sections. And it's pretty thin. When we start trig, chapter 4 is 2 separate packets. Because the first 4 sections are like the intro, and then the second 4 sections are the applied.
That's like the whole packet for a
So,
month.
oh, I love it. It's my favorite thing.
Your favorite
It's like, what if I just drop out for that?
It's my favorite thing.
What's your favorite team?
Yeah.
Oh,
I love factoring and trig. Like when you can factor in trig, oh, that's exciting.
That's when everyone gets an A.
All right, so if you look at the first page, we're going to graph by hand without a calculator. Unless it says to use a calculator, we will not be using one. And I think like the last couple of problems that we drew today, it'll say use a calculator and round to 3 decimals. So we are going to look at exponential functions and really kind of just reintroduce the shape of them, why they move, what features, what important parts do they have, their characteristics. So we have 2 different exponential cases here. The first case with a positive exponent, the graph underneath. The second case with a negative exponent and its graph underneath. Just get you like to kind of see what happens one positive, one negative. How do you graph an equation by hand? If you don't know any of the characteristics or remember what it looks like, and it's not something easy to think about, make a t-chart. So we're going to go back to making a t-chart.
I might drop out now.
Might drop out.
I don't
Heaven
have
forbid,
time for
t-chart.
trig.
So we're going to go back and make a t-chart because this isn't a line.
No, definitely.
I can't just get a quick y-intercept, y equals mx plus b. It's not a parabola. I can't graph it quickly using h and k. So we have to make a t-chart. Those 5 little numbers that we use in our t-chart. And then again, no calculator. Use that mental math. If I plug in an exponent of -2, what does a negative exponent do to the number? Rebecca? It does make it a fraction. So it takes that negative exponent and pulls the value, places it under 1. And then we have a positive exponent. Rebecca, what is 1 over 2 squared? 1/4. You can do that without a calculator. So a negative exponent just bumps it to the denominator under 1. So Rebecca, 2 to the -1 is? 2 to the 0? 1. And then 2 to the first is 2, 2 squared is 4. And we plot these 5 points. So 1/4 and 1/2 are pretty close to each other. This means you only have a tiny little box to begin with, so those 2 numbers are pretty close. And then it starts to increase. We say that this is an exponential function. If something grows quickly, we say it grows exponentially. So if I used a 3, I'd be up at 8. If I used a 4, I'm going up to 16. So the distance between my points get more rapidly, like further away from each other. When you connect these, how would I connect the values beyond the points? Kevin? Yeah, so it just skims along the axis. Oh. Yeah. And it does have one, just like an asymptote. It does have an asymptote. So the graph just skims along the x-axis because that's where you have a horizontal asymptote. It can never be 0. There's no way that I can take a base of 2 to some kind of exponent and make it 0. Because 2 to the 0 is 1. 2 to any negative number is just going to be a very small fraction or a very small decimal. So it just skims along the asymptote, goes to infinity or negative infinity in this case. So see if you can do the next one. Again, the goal is to see what happens if you have a negative exponent. So what should happen? What's going to change with the graph? Jacob, what y values did you get?
I got 9, 3, 1, 1/3, and 1/9.
Yeah. So now because we have a negative exponent and a negative x, it actually makes it positive. So this graph starts up high, and then it decreases and it moves lower. Jacob, does it still have an asymptote?
Yeah, it's still
Yep.
x-axis.
So just because we're making a negative exponent doesn't change the fact that we still have this horizontal asymptote. So the questions underneath are just asking you to kind of analyze the graph like we've been doing. So domain, range, x, y, intercept. Graphs all have that same information. Those are characteristics of graphs that every graph has, no matter what the shape is. So Quinn, I'm going to pick on you. What's the domain?
For the first one,
Both of them. I think they have the same domain.
parentheses
Left and right.
negative
Yeah.
You know, I fought for that. I just got the number wrong.
I'm a clean leader. Like a cheerleader, I'm a clean leader.
Quinn, what would the range be? Looking up and down. So where does it start? Horizontal, like vertically. What value does it start as? Is there anything underneath there? No, so it's all above what number? 0. And it goes up to? Yeah. So it starts at the y value of 0 and everything's above it. So 0 to positive infinity. The next two questions, x and y intercepts. Maya, what's the x-intercept? How about the y-intercept? Yeah, they both have that. Because any power of 0 always makes the number a 1. Doesn't matter what the base is. Horizontal asymptote. That's my y equals 0, the x-axis. And then, are they both increasing, both decreasing? What's going on with these graphs? Go Jeff, what's going on with them? Yeah, so the increasing function would be the 2 to the x. The decreasing is the 3 to the negative x. A negative exponent makes it go down. Just like a negative slope makes it go down. So negative exponent makes it go down. Alright, so 1 to 1. We talked about 1 to 1 back in chapter 1. And there was a reason we talked about functions being 1 to 1. So we know it's a function, but what does 1 to 1 mean? Yeah, do you remember why we do the horizontal test? Phone a friend, Connor.
It's like the test that each y value only has one x value.
So test each y has one x because, Ellie, we need to know if it has an inverse. Good. See, we all work together in here. So Emma, does this pass the horizontal line test? It does. And I know it's hard to see because it looks like this is just going to go horizontal, but like it really does continue to decrease. It's decreasing such a tiny little value that physically we wouldn't see it and it looked like it'd be horizontal. But this continues to decrease a little teeny tiny bit each time. So it is 1-to-1. Both of them are 1-to-1. And both of them will have an inverse because that's why the log exists. So the log exists because it's the inverse of the exponent. So yes, they are 1-to-1. Yes, it's a function. Are they continuous? Maggie? Yeah. There aren't any poles. There aren't any asymptotes vertically stopping the graph. And then they both have what point in common? 0, 1. They don't have any other common points, just at 0, 1. Questions? Not so bad graphing them. So at the top of your page, you have the number e, and then we have a couple of properties to look at, trying to refresh how a graph moves. But the number e is like the number pi. We call them irrational numbers because they just kind of continue on and on and on forever. It's also called the natural base because it goes along with the natural log. So something that has a base of e means you don't have a number here. I don't have a 2. I have an e. Does anybody remember what e is? Kevin?
Is it 10?
It's not 10 because that's the common one. Ellie? Oh, you're good with the 2 point.
6.
Connor?
2.8 something.
2.8 something? Maria?
I thought it was 2.14.
That's 3.14.
I got this.
Jacob?
2.63. Oh.
2.718?
I knew there was 8 in somewhere.
I totally guessed that.
Last year we had a chart, a big exploration. It was a chart, and we were doing compounding interest.
Oh,
And we compounded to like the 10 times, and then we compounded 100 times, and then we compounded daily, and every minute, and then every second. And eventually it just kept getting close to 2.718.
Yeah, we did.
I had a note.
What?
No.
This game.
Maybe.
This one?
Oh yeah. Oh no. Oh, but you still have that crazy chart.
That was
That's the standard normal curve chart.
I love that. I just still want that chart.
All right. He still has that chart.
I still want
We got a new one.
Yeah.
Common powder sheet.
You should play Pluto.
All right, so let's look at the questions underneath. Again, without actually graphing in your calculator. If I want to describe or explain a transformation, how does the graph move? How does the graph shift? How does it reflect? So thinking about everything we've done with graphs in those 2-3 chapters, because we did chapter P too. If I have 3 to the x plus 1, what happens to the graph? Do you remember, Taylor? Ooh.
Right.
Ooh.
Okay, I give up.
It's gonna
Something with 1. Jacob?
It's gonna stretch.
No. She's closer. Abby. Left 1.
Oh.
Remember, when it's with x, x moves the graph left or right. It doesn't matter where the x is. If it's as an exponent, if it's squared, if it's underneath the square root. But this is really saying x minus a negative 1. Or that was supposed to be 1. So that's your h value, because it's always x minus h. So x minus the negative 1 moves it left. Jacob.
Why wouldn't it be stretched? Because like, so say you have a T chart, it would be like 3 to the, or yeah, 2 to the second plus 1, so it'd be 2 to the third, which would make it go higher. No?
No. Because this is just moving your x
Oh.
left.
Okay.
So I understand how you're thinking, but it is just shifting. Like if we graph this compared to the other one, it is just shifting it left.
Okay.
Letter B. So if I have 3 to the x and then minus 2, Dylan, what's going on with the minus 2? Dylan S.
Down 2.
Down 2. So this one moves it down because the 2 is away from the x, separate from the exponent and the base. So that's going to just move the graph down. It's shifting it down 2. Skip letter C and look at letter D because this is the one we graphed on the other side. What happened to that graph, Odette? Oh, sorry, I thought you were raising your hand. Yeah. Because you're making x negative. So if you're making x negative, x is positive, I'm the y-axis, now it's negative. Flipped over the y-axis. And then the last one, if you make y negative, it flips over the x-axis. So if y is negative, it's flipping down. If x is negative, it's flipping left. Questions? So we have 3 little properties, not all of them, there are like 8, but just these 3. If you have a to the x times a to the y, Mariella, what happens a to the x times a to the y with those exponents? Remember what that property was? How do I combine them together? Yeah. So we add the exponents when the base is the same. If you have a to the x to the y power, what do you do with those? Multiply them. And then when you're dividing, you subtract. So instead of just doing a whole bunch of exercises, adding and subtracting exponents, this one's a little more interesting because it gives you 3 equations and it wants you to kind of decide which one of these functions are the same, if any of them, or which pair of them would be the same, or all 3 of them the same. And it says for you to try and use the properties of the exponents above. So I'm going to help you out a little bit here since we're almost out of time. We're going to try and go backwards with the properties, and I'm going to pick the middle one. So if I look at the first property, I currently have x plus y because I have 2x plus 6. How could I go backwards and pull it apart? Kevin, what would that look like?
2 to the 2x plus 2 to the 6 times 2 to the 6.
Yeah. So instead of condensing it together and adding them together, we can do the opposite and expand it as well. So plus means I could break it apart into the separate bases. The middle property, if I have x times y, it says I can also rewrite that. So my 2 is going to be squared, and now the x is separate. And that's based off of the middle property. So I'm just like working backwards with the property instead of condensing it together. So Kevin, what is 2 squared?
4.
And 2 to the 6th is? Which one is it the same as? H. We could have also started with H and worked through it similarly as well. For letter F, f of x is 12. Can I write 12 as a base of 2 or a power of 2? No. So that one is not the same as the other 2. The last couple of problems are just plugging it in your calculator. I think you can handle that. Just make sure you remember E is with the LN. Part of your homework is the next page in your packet. There are some graphs so that it eliminates questions that Jacob says, because he was saying, like, how does it do that? Why does it move left or right? And it should really move the graph up or down, and it should stretch it. So the goal of that worksheet is for you to see the properties and where those numbers fit and how they kind of apply to the graph. Your homework is due on Tuesday. So there's a couple problems in the book, and then there are 8 graphs in your packet on pages 5 and 6, and that's due on Tuesday. Questions?
Oh, just kidding.
Yeah.
Get a chance to look